So thank you all for joining. Today, I'm going to talk about a few different ways that we can use spectral methods to solve differential equations. This is in some ways a natural continuation from Tom Morrison's talk from a couple months ago. So Tom talked about how we can approximate and interpolate functions fairly accurately using Chebyshev polynomials. I will be talking about different ways in which we can use Chebyshev polynomials and their generalization to solve both ordinary and partial differential equations. So I'll be focusing on fairly simple differential equations that have the form of some operator acting on the solution, which is subject to some forcing function f. I'll assume for now that this is a linear operator. This is not a necessary assumption. There are ways to deal with nonlinear equations and spectral methods, but I don't want to get into that today. I'm also going to deal just with ordinary differential equations. So we'll assume that our solution is just a function of one independent variable, which we'll call x. And then similarly, our forcing function will be some prescribed function that is also a function just of x. The basic idea behind the spectral method is to assume that we can expand our solution in terms of a summation over some constant coefficients multiplied by some suitable basis functions phi j. We can make a lot of different choices for different phi's. In most cases where you have a finite domain, so a domain with definite endpoints, Chebyshev polynomials are almost always a good choice, or at least not a bad choice. So Chebyshev polynomials, just to remind you, they have can be computed in terms of a trigonometric identity. So that the Chebyshev polynomial of degree n can be computed as cosine of n sine inverse of x, where here x is some value within the domain -1 and 1. I want to mention that we're not limited to looking at differential equations that are only considered in this domain. I'm mostly dealing with stars these days, and in that case, we make a mapping to some radius in the domain 0 and 1 or 0 to infinity. And so we implicitly be considering Chebyshev polynomials that are still just a function of this x, which is in -1 to 1, but this is implicitly related to another radial domain. I won't talk about that today, but that's just something to keep in mind. You're not limited to that radial extent. There are a lot of other different options that you could use depending on your situation. If you have a system that is periodic, for instance, it might make more sense to use Fourier modes. If you're working on the surface of a sphere, you might use Legendre polynomials or spherical harmonics. Another option that has not at all been popular until a little more recently is to use what are called Chebyshev polynomials of the second kind. So these are usually written as some un, and they can also be computed in terms of another trigonometric identity. It's right here. And like I said, they haven't been used a whole lot until the last couple of years, and I'll come back to why a little bit later. Any basis functions that are useful will be orthogonal, so they'll always satisfy some orthogonality relation where here these brackets denote an integration over some weighting function. For Chebyshevs, this is 1 minus x squared minus 1/2. And this will either be equal to or proportional to the Kronecker delta. So you want basis functions that are as unrelated to one another as possible. You don't want them to have any spatial overlap, because the main advantage of a spectral approach is that hopefully you only need a few basis functions to very accurately describe your solutions. You want a linearly independent basis to start out with. So once we have chosen a basis for our solution, the main goal of any spectral method is to compute these coefficients. Because once we do that, we are done. We have a description of our solution we can plug into whatever we want. I'm going to start just by mentioning some historical approaches to this, and then I'll move on to some more recent results. So one method that many people will associate with or call the spectral method is a Galerkin approach. This basically boils down to making our spectral expansion, taking an inner product with a arbitrary member of our basis set, and then deriving a set of algebraic relations. So I'll go through how that works. So we insert our spectral expansion into our differential equation. Because I'm dealing with a linear operator, I can take this summation outside. Similarly, these are just constant coefficients. So all we're left with is our operator acting on basis functions, which is our forcing. And then the main idea behind a Galerkin approach is to take an inner product with some arbitrary phi I, where here I is not necessarily equal to j. And then do the same thing on the right-hand side of your equation. And what you're left with is a matrix equation that has the form of A operating on a vector of our coefficients. This is what we actually want to solve for. And then this is similarly equal to a vector of the projections of this function f onto our basis set. And so here, that just to say this explicitly, our individual elements of our matrix Aij are just these individual integrals between the arbitrary basis function, the arbitrary basis function that we're integrating over, that defines the rows of the matrix, and the columns are defined by the linear operator acting on basis function. Since we're dealing with differential equations, we need to impose some boundary conditions. The easiest way to do that with the Galerkin approach is to use basis functions that already satisfy those boundary conditions to begin with. Or if something like Chebyshev polynomials don't satisfy those boundary conditions to begin with, you can take linear combinations of them that do. So for instance, if you want to impose the constraint that u at plus or minus 1 is equal to 0, then you could make an expansion in basis functions that are defined in this way. Because these, subtracting the first and second Chebyshev polynomials from Chebyshev polynomials with even and odd degrees automatically sets them equal to 0 on the boundaries. So then you don't have to worry about boundary conditions at all. Another option you can take is to add additional rows to your matrix that enforce those constraints. Yeah. So please, yeah. Polynomials. So they are. So this is actually a polynomial in X. This is just this trigonometric definition is a useful way to compute them. So this Chebyshev polynomial with a given degree n is a degree n polynomial. So it has some form. Goes up. It's a polynomial expression up to some time. This is just a useful way numerically to compute this. They're basically projections of Fourier modes onto a finite domain. So their Chebyshevs are as useful on finite domains as Fourier modes are on periodic domains.
Also, your normalization, you wrote out normalization. Normalize that square is cut off concepts. So physical system usually have zeros.
Oh, you mean for the inner products?
Yeah.
So usually for the integrals, you'd actually take the weighting involves weights that would be 0 at those actual endpoints.
That's physics.
Yeah.
So
Yeah, so that's the basic idea behind the collocation method. A downside of this approach is that this matrix is almost always dense. So unless your basis functions are already eigenfunctions of this operator, in which case you're sort of already done, this matrix will be dense, and that means that if you go to truncation of your system at some n that is very large, then it can take a long time to invert this matrix and complete your solution. There's some other problems associated with that I'll come back to. A related but separate approach, something called a pseudo-spectral method, or spectral collocation. Spectral collocation basically involves, rather than working in coefficient space, you work on some special grid space. So we still start out by making an assumption that we're expanding our solution in terms of some set of basis functions, except that in this case, we assume that if we truncate this summation at some degree n and evaluate this expansion at a specific set of collocation nodes, that this equality is exact. So just to plot that visually, you have interval from minus 1 to 1, and this is u. If you have specific collocation nodes, your solution might wander around a little bit, but at those nodes, it will be exactly equal to this truncated expansion. The appropriate choice for which nodes to use are, in the case of Chebyshev's, they're basically the extrema or the roots of the nth degree polynomial. So, for instance, if we have n equals 3, then we would either take the 4 points that are they should be at the same level, sorry. 4 points that would be the endpoints in the extrema of this polynomial, or we would take the roots. You basically would make a choice between those two based on whether or not you want to include the endpoints in your calculation. So if we make this expansion, we basically already have a matrix equation to begin with. So substituting this into our differential equation, we don't actually need to take any intervals for this is already a matrix expression. So for instance, if we had the differential operator just d by dx, then this matrix would take the form, the overall matrix equation would take the form of T0 prime, so I'll denote derivatives with respect to x by prime, evaluated at x naught, T1 prime, evaluated at x naught, so on and so forth, down to the last Chebyshev polynomial. And then the next row, so this would be a row corresponding to x naught. The next row would be corresponding to the next grid point. And so on and so forth down to our last grid point. And so this is kind of nice from a programming standpoint because it's fairly easy to construct these matrices without needing to take any intervals. So you just have your expression already. This also leads to a fairly natural way to impose boundary conditions. So, for instance, let's say you wanted to impose that u of -1 is equal to, I guess, +1 is equal to 0. The Chebyshev points run backwards. So the first point would correspond to all those. The first point in the Chebyshev grid corresponds to +1. And so all you need to do to impose that boundary condition is to, instead of putting these derivatives here, we put the actual basis functions. And so then this row acting on our vector coefficients, we would set, rather than f evaluated at the first point, we just set that equal to 0. Leave the rest of the rows as is. And so this acting with this row gives you 0, and that imposes your boundary constraint already. The downside is, again, that we have a very dense matrix. So as you go to larger and larger n, the evaluations of these derivatives can get very, very large. And so that can lead to some numerical inaccuracies just in actually constructing this matrix. You also increase the condition number of the matrix as you go to larger and larger n in your truncated expansion. And so the condition number basically tells you how much, if you have a small change or a small inaccuracy in f, how much is that going to change what you compute for the solution? So if you have a really high condition number, that can potentially lead to some inaccurate solutions for your coefficient vector. And so that's not great. In practice, for most problems, that's not really a big deal because spectral methods are memory minimizing. So for a given accuracy in your solution, you typically require an order of magnitude less grid points than you would for something like finite differences or another method. So you don't usually need a very big n, so that the condition number doesn't get that bad in most cases. But there are certainly problems where you might have singularities, for instance, or some small perturbations that lead to really strong variations in your solution, where you really need a large number of Chebyshev polynomials in order to accurately resolve your solution. But actually constructing the matrix that involves those can lead to some numerical problems.
Is it always necessary to pick a definite n as opposed to have some spectral window function where low order things are more important, higher order?
I mean, the typical method for doing this is to start with some n, double it, and see if your solution changes. And usually you don't need to do that too many times before you get to some convergence. But there are some problems where you do. Any other questions about this before I begin?
If you're adding boundary conditions or pressure conditions on it, does that matrix necessarily have to be square, or can it be?
It doesn't need to be a square matrix. Yeah, I mean, you can end up over determining things if you don't have a square matrix.
So then you wouldn't necessarily have to pick all the roots, so you pick all the in that case, or
Oh, well, so choosing, if you chose the roots, then you would not need to explicitly impose this boundary condition because your evaluations of the differential equation don't involve the boundaries. So in that case, you would need to make sure that the Chebyshevs actually satisfy the boundary conditions that you want to impose already. So if you just need the solution to be regular, then that's fine. You don't need to impose boundary conditions again. But if you have a specific condition on the boundary, then it's probably better to use the extreme endpoints grid.
So I had this question from 10 years ago when a student wanted to do this. You use this collocation method to generate a bunch of large n matrix. They generate lots of spurious solutions. Do you know that problem?
That's more a problem of linear algebra than the spectral method. So yeah, if you make a matrix that has some large n, or if you make an n by n matrix, you are going to get n eigenmodes, for instance, if that's the problem you're dealing with. And yeah, so as you get to any oscillations that are close to, say, half the number of grid points, you're going to end up with a lot of solutions that are just they're eigenmodes of the numerical matrix, but they're not eigenmodes of the physical problem.
Because you did a couple.
Yeah. So a fairly typical problem, if you use this collocation method, you'll often end up with solutions that, if these are your grid points, they oscillate on this level. Those are not resolved, so that means you need to have more n.
I think that's a problem that comes up when you do the eigenvalue
Yeah.
problem of this.
So
If you do the what? The Galerkin method should actually be almost equivalent to the collocation method if you're using, so if your grid is the same grid you'd use for quadratures in the Galerkin method, they're almost equivalent.
So if you try to do an eigenvalue of this, or an eigenproblem,
So if this f was 0, and this was some.
so what you end up getting there is you'll get all of your eigenvectors, which you can then plot as functions, because but those functions don't necessarily resolve the eigenfunctions of the continuous solution.
Yeah.
So the first, if your eigenfunction has few enough oscillations to be resolved by your polynomials, then you'll get it, but then after that, they don't match up.
It's worse on
Okay, so yeah, so the main downside of this is the denseness of these matrices and the fact that you can get some numerical problems as you go to really large. And that problem is to some extent addressed by a newer spectral method that's been developed in the last decade or so. And this is something called an ultraspherical or Gegenbauer polynomial method. Yes, yeah, I'm not going to write that up. we'll get there. So this basically stems from relationships between the Chebyshev polynomials of the first and second kind, and then as I'll get to later, the ultraspherical or Gegenbauer polynomials. So the main thing to note here is that the derivative of the Chebyshev polynomial of the first kind is directly related to a Chebyshev polynomial of the second kind with the degree differing by 1. So that means that if you have a solution that you have expanded in regular Chebyshev polynomials, then you can represent its derivative in terms of the Chebyshev polynomials of the second kind. So this summation would start at 0. This one would start at 1 because all the Chebyshev polynomials all have a constant first. The first polynomial is constant, so the derivative is 0. And so you can actually write this as a matrix operation. So if we have some truncation at a degree for our solution, then this is approximately equal to some matrix acting on, again, our vector of coefficients, where this matrix D0 has, because we're shifting degrees by 1, has the first column, these are all zeros, and we have a 1, and then everything else in this row is zeros. The next one down on the diagonal, or just off the diagonal, is 2, 3, and so on. And so we have, this goes all the way down to n minus 1 zeros on the bottom row. And then this is, we started with our regular coefficient vectors for Chebyshev polynomials. So this is really cool because the matrix here is almost diagonal. It's incredibly sparse. It only has non-zero entries just off the diagonal here. And these values are also relatively small. So before, if we needed to take a derivative of these Chebyshev polynomials, actually constructing a matrix of these values would lead to values that are really, really big. And that's not the case here. So if we have, let's say our f14 function is expanded in terms of the Chebyshev polynomials of the second kind, where I've included a hat here to show that we're expanding the polynomials of the second kind rather than the first. Then all we need to do, let's say assuming our differential operator is just d by dx. And all we need to do to compute the solution is invert this very sparse matrix, which is much easier to do or can be done more quickly because it is so sparse. You'll notice that this bottom row, these are entirely zeros. And that's again because as we take the derivatives of the Chebyshev polynomials of the first kind, we go to Chebyshev polynomials of the second kind that have a degree shifted by 1. And so that moves us up 1 row. So this row is basically useless, and it would give us a singular matrix unless we replace it again with boundary conditions. And that makes sense here because we have a first order differential equation, so we need 1 boundary condition. So we can use the same approach as in the spectral collocation and replace this with some boundary condition either at x naught or the last one of the boundary, whichever we're imposing the condition on. And so what people normally do is they permute this row to the top, because then you end up with a matrix that has an almost diagonal structure, which is numerically nice to convert.
So even if you don't introduce this U concept, the derivative is still very narrow.
So if you so the spectral collocation method, if you just kept in Chebyshev polynomials with the collocation, that the matrix would be dense. Yeah, because the t not prime, all of the tn prime of for all the xi, these all have non-zero values for any degree n and any point within the collocation grid.
Still just true out of course the other Chebyshev next door.
So if you take instead of so this is if you evaluate the Chebyshev derivatives directly through the spectral collocation method. If you take the inner product with some Tij as in a Galerkin method, then you would end up with a matrix that is I think upper triangle. So everything below the diagonal is 0, and then everything above it is non-zero values. So it's still much more dense than the matrix we get by switching to these Chebyshev U polynomials. The major complication that is introduced with this approach is if we have to think about any spatially varying coefficients in our differential equation. So if we want to include some coefficient that has some dependence on x, then to use this translation between Chebyshev T and U polynomials, then you have to represent the product A of x times U of x as not just a expansion in Chebyshev T polynomials, but an expansion in Chebyshev U polynomials. So that ends up looking like in practice is the application of a few matrices. So I'll write this out in terms of summations to be clear, hopefully. So you can write this in terms of 2 matrices. So the first one, this S naught here, this translates from coefficients in a Chebyshev T basis to coefficients in a Chebyshev U basis. And then the second matrix, M, which I've included A in brackets to show that the form of this matrix depends on A. This is a multiplication matrix that allows you to multiply these 2 functions in coefficient space as opposed to in physical space. And so this gets a little complicated. I don't want to go into too many of the details, except to say that both of these matrices are sparse as well. So the S naught matrix has values that are just on the diagonal and just above the diagonal. And this MA, how sparse this matrix is will depend on the specifics of your non-constant coefficient. So if this this requires a lot of Chebyshev coefficients to accurately describe the non-constant coefficient. That will increase the bandwidth of the non-zero values in this matrix. But usually for most coefficients, you don't need very many Chebyshev polynomials to accurately describe them. So the bandwidth of this matrix will be relatively small. And so the upshot is that you can still form problem matrices that are, relatively speaking, fairly sparse. Any questions about that before I move on? The last bit here.
Presumably, for change of variables, it decreases the bandwidth as well. X.
Yeah, I mean, that will depend on the coefficient. For different problems, whatever functional form of A is, there might be better or worse ways to.
How does the computational complexity of getting this is depend on the bandwidth of the diagonal band?
It's easier to invert matrices that are closer to diagonal. Because if it's diagonal, then you're done. So the sparser the matrix is, the faster it can be.
I guess we can
The main trade-off is so you have much less complicated derivative matrices. You have much more complicated multiplication by these non-constant coefficients. So with the collocation method, multiplying by these non-constant coefficients is trivial because you're just multiplying by them at each grid point. But in this case, you have to do this multiplication in spectral space in not just one basis, but multiple bases. And so that's the complication. So this is a way to solve differential equations that are first order, so they only involve one derivative. There is a generalization to differential equations of arbitrary order, and that involves what are called these ultraspherical or Gegenbauer polynomials. So a Gegenbauer polynomial, they're often written as some capital C with some order lambda and a degree k. So this k here is the polynomial degree, as with Chebyshev polynomials or other polynomials. This is an order that describes a different set of polynomials for each lambda. So it turns out that the Chebyshev polynomials of the second kind are the first example of these Gegenbauer polynomials. The useful thing is that, as with Chebyshev polynomials of the first and second kind, there is a relationship between Gegenbauer polynomials of a given order, their derivatives, and the Gegenbauer polynomials of the next order up. So you can write that as so we have a direct relationship between the derivatives of each of these Gegenbauer polynomials and the next set of polynomials, but with degree again shifted by one. So this is a very similar recursion relation. So this means that if we have derivative of order lambda of our solution, then we can first of all use the relationship between the Chebyshev polynomials of the first, and I'll write this with k's instead, of the first and second kind. Yeah. So this is the derivative relationship that I wrote earlier. But then, because these Chebyshev polynomials of the second kind are actually the first instances of the Gegenbauer polynomials, we can write this as another summation And this, sorry, this doesn't start one. So these factors out in the front, these come from the repeated application of this recursion relation. So we get a 2 to the lambda minus 1 times, and then similarly we have every time we apply this recursion relation, we're multiplying by the new lambda. So this gets a lambda minus 1 factorial. The summation will now start at lambda because each Gegenbauer polynomial, the first of them has a 0 derivative, and we're decreasing the degree by 1 each time. So we end up eliminating the first entries in each of these summations each time we go to the next set of Gegenbauer polynomials. But the point is that we now have an expression for our derivative of arbitrary order of our solution in terms of direct series expansion in these polynomials, which are themselves orthogonal again. So whatever differential equation we have, we can construct a matrix representation of it that is going to give us nearly diagonal matrices to solve. So I'm going to just give a basic. I won't go through all the details of the different transfer matrices that are involved in this, but if we have, so for instance, a differential equation of order E, then we can come up with a matrix representation of this differential equation that looks something like this. So we have a bunch of nearly diagonal matrices. These are all dotted with what is still a vector of coefficients in our Chebyshev T basis. And then these are again equal to just a bunch of transfer matrices applied to again a vector of our forcing that is still in the Chebyshev T basis. So even though actually constructing this matrix is really complicated, it involves these multiplication matrices that are different for each coefficient because we're for each derivative we take, we're transferring to a different basis of Gegenbauer polynomials. We also have these transfer matrices that this basically goes from Gegenbauer basis of order lambda to a Gegenbauer basis of order lambda plus 1. Once we actually construct this matrix and invert it, what we get back is still the coefficient vector of coefficients in an expansion in these regular old Chebyshev polynomials. So we're implicitly using a spectral method that involves these much more complicated series of Gegenbauer polynomials, but you don't actually have to deal with that once you compute your solution. So in the end, you end up with problem matrices that look something like this, where you have, if you have an order P differential equation, you have P rows that have all been 0 and moved to the top, and then you have a band along the diagonal that is non-zero. And like I was saying, how wide this band is will depend on these non-constant coefficients and how many basis functions it takes to describe them. But in any case, this is a sparser matrix than you would have in a spectral collocation or a Dewberry method. And the condition numbers are generally better. So that's a good way to approach the problem if you need really large number of Chebyshev polynomials in your solution. I will stop there. Take any questions.
So can I think of this one? I use Chebyshev. It's like more of a. Yeah. You're giving equal weight polynomials. So you end up trying to reduce the derivative plus the difference. By expanding their little. Really giving a lot more weight to that. And as a result, you're fixing the derivative better. So it's like bringing. Like if you take a fourth derivative of the Chebyshev polynomial.
Yeah.
But this is.
I think
Like you're now giving more weight out of the boundaries.
I think it can probably be described better as you take more derivatives, you're coming up with a more suitable basis to describe that.
Yeah, that's what
Okay, then yeah, that's
because literally.
yeah. So the Gegenbauer polynomials of consecutive orders are a better description of the derivatives of your solution than just the derivatives of the Chebyshev polynomials. And so what we're doing each time we take a derivative here is we're going up to another basis that is a better description of the derivatives. I think.
So if we want to go out into the wild, so that is there nice software for example, these transfer matrices.
Well, the transfer matrices are actually very easy to compute. So for instance, this is something like this, just things along the diagonal. The complicated part is computing these multiplication matrices. There's a MATLAB package called Chebfun that includes support for these ultraspherical methods. Aside from that, I think they also have Julian implementations.
Delegate linear algebra stuff. So they're favorite for handling matrices like this.
Well, for the linear algebra calculations, you can go to something just like LaTeX. Once you've made your matrix, there's a number of different linear algebra packages you can use.
The special options of the handling structure.
Yeah.
And there's tri-banded. I don't know if there is.
There are so for instance, there are different packages that are better for sparse things. Hetc has a lot of support for sparse matrices. Hetc and Slupc to go to for sparse things.
What's the context of this algebraical thing? Is it something new in the algebra and perspective?
People have known about these Gegenbauer polynomials for a long time. I think there just haven't been
Introduced.
they haven't made the connection to I mean, traversing bases like this is complicated to think about, so I don't think people really have gotten to do it in the last decade or two.
High side.
Or just the name, which is spherical complex.
I don't know.
What do these polynomials actually look like if you plot them? Like Chebyshev's a very nice pizza plus minus one.
That's a good question, and I should have looked that up. I actually have no idea, and that's sort of because this method does not require you to actually use the Gegenbauer polynomials. You're just implicitly using them in your construction of matrices. You don't need to know at all. Yeah.
Well, we take derivatives of a function.
Yeah, I guess they don't have to.
It's steeper, it's steeper, it's steeper.
But that property is actually quite useful to model the galactic potential.
Yeah, that's because this is why I was asking, you're not putting a lot of result when you do the version.
Do you have the weight as in your basis functions as opposed to in your matrix? I think yeah.
Something like that. Well,
You have small values
a
in your
different way to
matrix.
say it, so the standard shall be different. So that's what's the. You're dominated by the possible.
Yeah.
That is basically brings it. Because. And here presumably the. So you'll undo that, so the coefficients. Probably went back down the higher. I suppressed the lower.
Yeah, maybe.
Does this approach deal with the issue of, ringing and the high order solutions that was you were describing for them?
So, I mean, the issue of the ringing of the higher order solutions, that just means you need more resolution. But the problem is when you go to a problem, let's say you have, let's say your solution looks something like that. In order to get rid of the ringing, you need to go really high n. But actually going to really high n means that you're constructing a matrix that's not very well conditioned. And so this method allows you to include thousands to tens of thousands of points and still have matrices that are well conditioned. Good solutions. It also lets you go to higher order derivatives.
Probably out of left field. People pragmatically use relaxation methods, let's say the matrix is built predicted, and then you just have it as function. I know that there are applications some substitutes.
I have not used relaxation methods myself. I know a number of people who use. I'm not really sure of whether relaxation methods can be usefully combined with spectral methods. I don't really know that.
One thing people will use. Right, the problem is you have case where and take lots of case, it's we'll see what I'm saying. And so you'd be like, I don't know the exact solution. We'll often take and brings squishes all together, and then you condition.
Yeah, I don't know if it's about, but I was thinking that people have these, you can try and solve this program, and you can just put in something, as long as you buy the participation, whatever function you put in, the participation, or you let it, like the way function, you will settle to the ball.
Yeah, I don't really know.
I've seen one-dimensional relaxation.
Yes,
and
you
did
can.
two-dimensional.
I self-denominate show you. Relax. You have an issue there, you have to localize the wave function. That's the zero.
I mean, that is so. And I didn't talk at all about nonlinear problems. The general approach there is to use something like Newton's method, where you start with some initial guess of the solution. You iteratively minimize the residual. The differential equation is expressed in terms of this spectral method. And so that's Is that sort of what you?
I guess, yeah,
Okay.
I don't know if I do whatever.
Okay, fair enough.
The relaxation method is good for when you have blowouts and you have singularities. But I've only done one. Anybody knows about two?
In the context I know it is 3D, anybody, simply on interaction.
So relaxation.
Yeah, basically you have a many body Schrodinger equation, sitting on relativistic particles, have some interaction. They're basically like a big ugly matrix. And then they seed it with the class function that in the form of the system. As long as they have some space.
Settle down. Wow.
And so it's called quantum Monte Carlo, and then people use it and basically do this relaxation a bunch of times. Each one is like a noisy estimate, like you can paralyze the crap out of it. Beat down
each one of the noisy estimates, so we can find together.
Okay.
And I guess you could think of, sometimes we have like a dynamical system and evolve it for many dynamical times, and see if it sells interest in state, in some circumstances, it's effectively a relaxation method, but the damage is with dynamics itself.
So I didn't talk about time dependence at all. Usually for spectral methods, people will, if you're going to do a time dependent system of equations, though, unless that you expect the solutions to be periodic in time, we'll use spectral methods for the spatial dependence of the solution, and then a more standard integration scheme for the time dependence.
This would not be helpful.
Sorry.
This would not be helpful for the spectral hydro.
I don't see why not. I mean, you can use this for the spatial
No
dependence.
paradigm makes these slides.
If you need to do things quickly, then it is faster to have a sparse
You
matrix.
don't need to make
Depending on it depends on the approach you're taking for the time dependence.
its initial condition.
Well, but like so if you do like the most naive thing, only that I've ever done at all really, like you just give all these coefficients, you use them with some time, right? And then like there's a time derivative that acts on that, you derive amplitude. But if you have a really,
That's why I said, look at
right, but if you have
the coefficient changes time is the earliest step.
if you have a very complicated off-diagonal matrix, then as you're computing the time derivative of all these things, you have to sum all these different coefficients. And if they are canceling some very complicated way, then you have to sum up like 1,000 mode amplitudes to get some precise cancellation that's going to happen in the physical system. If you have a sparse matrix
Yeah, that does eliminate a lot of the solutions. And if you have things that are
So matrix
big and
works.
almost canceling, then that's
it's not a speed thing, it's consistent.
No more questions? Then let's have the speaker.